Hello everyone. Good morning. I'm Selma Yahia. I'm a PhD student at the University of Mohammed Bougara Boumerdes, Algeria. I'm here to present my research paper on the performance of MIMO Vehicular Visible Light Communications. First of all, I would like to thank the organizer and all the sponsors to provide me an opportunity to present my paper. This presentation is structured as follows. After the presentation of the problem statement and our objective, we present our system and the channel models. Then we show and discuss the numerical results. Finally, we conclude. So let's start. Over the past couple of decades, vehicular density and volume have increased dramatically, leading to a significant increase in congestion and accidents, with serious impacts in the environment. Intelligent transportation systems have received much attention as an effective way to improve road safety, travel efficiency, and passenger comfort. As backbone for ETS, vehicular communication includes a number of moving cars that establish a wireless communication with each other and with infrastructure along the road. The resultant connectivity forms are vehicle-to-vehicle, vehicle-to-infrastructure, and infrastructure-to-vehicle. So the current deployment of vehicular applications mainly depend on the use of radio-based solutions. However, in the near future, the widespread prevalence of ETS is highly expected, causing high interference levels in the corresponding limited radio frequencies. This often results in a low packet reception rate. Therefore, an alternative or complementary solution to RF technologies became necessary. So visible light communications is one of the most interesting solutions. It depends on the simultaneous use of lighting emitting diode LEDs as wireless transmitters and lighting devices. The increasing adoption of these LEDs in automotive lighting such as headlight, taillight, turn signals, and brake lights make the usage of Wi-Fi technology a viable option for vehicular communication. In comparison to indoor Wi-Fi counterparts, vehicular Wi-Fi faces additional challenges such as the mobility, the effect of weather, and the asymmetrical pattern of outdoor lights. Considering V2V forms, which is the focus of this work, and instead of using single transmission technique, multiple input, multiple output is considered as one of the effective techniques used to achieve high data rate. In vehicular networks, there are usually multiple sources of LED, so it's natural to use MIMO technology to have parallel transmission and improve the data rate. There are already some efforts suggesting MIMO Wi-Fi systems in vehicular applications. However, some of these works have used the ideal Lambertian pattern to model the car headlights, which does not reflect the reality since the practical headlights have an asymmetric radiation pattern. Furthermore, other works consider the only case where the cars move perfectly. In other words, no lateral shift between the cars is considered. The impact of the vertical and lateral shift, same as the effect of adverse weather conditions, should be taken into account for a precise analysis in real vehicular scenarios. So in this paper, we investigate the performance of the MIMO V2V Wi-Fi system, where two vehicles follow each other on a single line road. We construct a 2x2 MIMO transmission system utilizing two headlights of the source vehicle as transmitters and two photodetectors installed at the destination vehicle as receivers. For channel modeling, we adopt the ray tracing features of the Optic Studio software, taking into account the asymmetrical pattern of the vehicle headlights, the possibility of both vertical and horizontal displacements between vehicles, same as the effect of weather conditions. In the simulation part, the received optical power and the bit error rate are investigated for each MIMO link between the transmitters and the receivers. Now firstly, I'm gonna show you the structure of our proposed system. So as shown in this figure, we consider a V2V scenario in a single line road with a width of WL. The two cars follow each other with a separation distance of dx and a possible lateral shift of dh between their centers. A MIMO transmission technique with N transmitter and M receiver is considered. Specifically, the two headlights of the source car are adopted as wireless transmitters. On the other side, a pair of photodetector receivers, denoted by RX1 and RX2, are served as wireless receivers, which are placed at the rear of the destination car under the taillights. Both the two transmitters or receivers are separated horizontally by a distance dc from each other. For channel modeling, the main steps of our channel modeling methodology are illustrated in this figure. The three CAD models for vehicles and roads are designed and imported to the Optic Studio. The specifications of the CAD models, such as coating materials, reflectance, and the type of reflections, are defined. The specification of the light sources, like the orientation, the radiation pattern, the emitted power. Also the specification of the receivers, like orientation, fields of view, sensitive area, are provided as other inputs. After the simulation scenario is constructed, non-sequential ray tracing is run to generate an output file containing information about the path length and the received power of each ray emitted from the light sources and captured by the detector. Finally, this information is imported into MATLAB for further progression. Mathematically, let's denote LEG, the transmission distance between the EF transmitter and the GF receiver. The channel gain between the EF transmitter and the GF receiver can be expressed as follows. Here dr is the receiver diameter. These parameters are correction coefficients, and C denotes the extinction coefficient for a specific weather type. And now let's move to the simulation results. As shown in previous figure, we consider a V2V scenario in a single lane road with a width of WL equals 3.75 meter. We assume that there are two cars follow each other with a lateral offset of 0, 1, and 2. The total transmitted optical power is 10 watt. All the simulation results are listed in this table. Now in this figure we consider the clear weather and the receiver aperture of dr equal 1 cm to study the effect of misalignment, which means the lateral shift between cars considering different dh values. It's observed that the receiver power decreases with increasing intervehicular distance. This is due to the attenuation of light signal as it travels through the air is very large. It's also observed that there is a noticeable difference in the received power values between different MIMO links. for short distances. This is due to the difference on the horizontal locations. Even the two cars are perfectly aligned. This difference became very small and negligible as the distance increases. Next, to show the impact of the received diameter on the received power, we consider this assumption. We consider the clear weather condition and the perfect alignment case. It's observed that the received power significantly increases as the aperture diameter increases. This is due to the fact that the amount of the light intensity captured by the receiver increases when the receiving area increases. For example, the received power at dr equal 1 cm is 0 dBm. Considering dx equal 20 meter, dh equal 0 meter, and the link between the first receiver, the first transmitter, and the first receiver. This climbs to 8 dBm and 12 dBm for the dr equal 2.5 cm and dr equal 4 cm. Now in this figure we present the corresponding received power of the MIMO links under different weather conditions. Here we assume dr equal 1 cm and dh equal 0 meter. It's observed from these figures that there is a small effect of the weather for short distances, but it is significant when the distance becomes sufficiently large. For example, consider dx equal 10 meter. The received power for clear weather is 6 dBm. This reduces to 5.6 dBm and 5.5 for moderate and thick foggy weather. That induces a degradation of only 0.4 and 0.5 dBm compared to clear weather. On the other hand, for dx equals 70 meter, the received power is minus 11 dB for clear weather. This further reduces to minus 13 dBm and minus 15 dBm for moderate and thick foggy weather, with a relative difference of minus 2 dBm and minus 4 dBm with respect to clear weather. Now in this figure we present the BER versus the transmitted SNR with different lateral shift, while keeping the dr equal 1 cm and the clear weather. It is observed that the lateral shift has a significant impact on the BER performance, where the larger DH, the lower BER. This is due to the fact that in the perfect alignment scenario, the channel gain are quite similar, providing high channel correlation, while the reverse is correct for lateral shifts. For example, consider dx equals 25 meter. The recorded SNR at dh equals 0 meter is 35 dB. This reduces to 32 dB and 30 dB for dh equal 1 and dh equal 2 meter. Now at this stage I would like to run over the main points of this work. So in this paper we have investigated the performance of a 2x2 MIMO VLC V2V system using two headlights of the source vehicle as transmitters and the two PDs installed at the destination vehicle as the receivers. We use a more realistic channel model which is based on the non-sequential ray tracing, taking into account the possibility of both vertical and horizontal displacement between the cars, same as the effect of weather conditions. In the numerical result part, the received power and the BER are investigated for each MIMO link. The result demonstrates the ability of parallel data transmission for V2V systems based on VIC technology. This will enlarge the achievable data rate and could be investigated in our future work. So thank you for your attention.